So hello everyone, welcome back to my YouTube channel. So in the first video of mathematics, we studied vector spaces where we studied vector space, subspace, spanning set, dimension and basis. So now today we'll be practicing questions of many types which will be enough for your exams. So let's start with the first question. So your first question says, show that V is equal to R square is not a vector space. We have to prove that it's not a vector space over the field R with respect to the operations of vector addition and vector scalar multiplication. So let's see. So how will we solve this? We have to, as you know, we have to show all the 10 properties that we had seen earlier. So first property was closure under addition. So in this, we assume let A comma B and C comma D belongs to R square, and therefore A plus C comma B plus D will also belong to R square. It is given as a property of vector addition. So by this we can say that it's satisfying the property. If we say some real numbers are belonging to that set, so their addition will also belong to that set. So next, commutativity of addition So in this we'll say A comma B and C comma D belongs to R square. Therefore C comma D plus A comma B will be equal to C plus A comma D plus B, which will also be equal to A plus B plus C plus D. What will be the answer to this? A plus C comma B plus D. So their addition can be reversed also, but you'll get the same answer. Therefore, this is also satisfied. So next, third one is associativity of addition. So let's see. So A comma B plus C comma D plus E comma F. This will be equal to A plus C comma B plus D. How? This taking this bracket first and then taking the next part. Com plus E comma F. Now when you'll apply the property taking this as 1 and this as 2, we'll get A plus C plus E comma B plus D plus F. Now similarly, when we say A comma B plus 2 brackets C comma D plus E comma F, what will we do here? Let's see. Let me erase this part. I have less space on this slide. So yes. So here we can say that A comma B plus C plus C comma D plus F. And when we take this 1 and this as 2, we get A plus C plus E comma B plus D plus F. It is same in both cases, the answer that we had proved earlier in this one. So therefore satisfied. So now let's go on. So our fourth property is existence of zero vector. So let's say your A plus Z1 comma B plus Z2 will be equal to A comma B. When is this possible? This is only possible when Z1 is equal to 0 and your Z2 is equal to 0. Therefore 0 comma 0 vector is there. Fifth property, additive inverse. Additive inverse is So fifth is additive inverse where we see a plus x comma b plus y equal to 0 comma 0. When is this possible? It is only possible when your x is minus a and your y is minus b, which is minus a comma minus b, and this is your additive inverse of a comma b. So therefore property satisfied. Sixth property, closure under scalar. There is a k into a comma b will be equal to ka comma b. This is belonging to R square. Seventh property, distributivity over vector addition. So k into a comma b plus c comma d is equal to k of a plus c comma b plus d, solving the inner bracket, and then we'll have k into a plus c comma b plus d. This is b plus d. Then we'll say, let's solve for this k a plus b plus k c comma d. This will get us k a comma b plus k c comma d. Then we'll get it as k of a plus c comma b plus d. Here equal in both cases. So eighth property, distributivity over scalar addition. So two scalars k plus l into a comma b will be equal to k of a comma b plus l of a comma b, then k a comma b plus l a comma b. Then we can write it as ka plus lb comma 2b. Then k plus, now let's distribute them and add. So k plus l into a comma b. Now let's assume this as a scalar. So we can write it as k plus l into a comma b. Then we can write it as ka plus l. Just open the brackets. Is it equal to 2b? And this is fine, but this is not fine. Therefore, eighth property failed. Therefore, not a vector space. You can write that. But let's solve for ninth and tenth property also. Associativity says KL into A comma B is KLA comma B. And your K into LA comma B will be equal to same KLA comma B. This is right because first LA and then KA will come, then it will get again multiplied. So KLA. Then I'll solve the 10th one also here. So 10th one says element of scalar multiplication. Here we say 1 into A comma B is equal to A comma B because 1 into A is equal to A and 1A comma B. This will equal to A comma B. So this is our first question. So this is the answer. Therefore, this is not a vector space. So now next question. So next question. This is saying let S be the set of solutions of the differential equation f double derivative plus f is equal to 0. Show that S is a subspace of f where f is the vector space of all real valued functions defined on R. So let's start solving. So first, we have to prove zero vector. Is it satisfying this? So let z of x equal to 0 for all x's belonging to R. Now we are given that f double dash plus f is equal to 0. Therefore, z double dash x will be equal to 0 and your z of x is also equal to 0 when we take this as our function. So therefore, z double dash plus z will be equal to 0. Therefore, it is belonging to S. Second, closure under addition. Addition. In this, we are saying f comma g belongs to S. Therefore, f plus g will belong to S. Now, we have a property as f dash plus f double dash plus f is. So, therefore, f double dash plus f equal to 0 and g double dash plus g equal to 0. We'll have to prove that f plus g double dash plus f plus g is equal to 0. Therefore, we can write this as f double dash plus g double dash plus f plus g is equal to f double dash plus g double dash plus g. So 0 plus 0 will be equal to 0. Therefore, f plus g belongs to S. Next, closure under scalar multiplication. Under scalar multiplication. So here we are saying if f belongs to S, then CF will also belong to S. So f double dash plus f equal to 0. So f double dash plus f equal to 0. Now we have to show that FCF double dash plus CF equal to 0. Now CF double dash C can come out as it is a constant. So take C common, you get F double dash plus F. Now this is 0, so 0. It is equal to 0. Therefore, as these three properties are satisfied, therefore S is a subspace. S is subspace of F. This is our answer. Next question. So this is our next question. So let V be the vector space of all 2 into 2 matrix A, B, C, D over R. Show whether these set of are subspaces of V or not. So first part says that W1 consists of all matrices with zero determinant. So first part. So your zero matrix 0, 0, 0, 0 is equal to 0. Therefore it belongs to W1. Now consider a matrix A and B. A and B belongs to W1 such that your delta of A1, A is equal to delta of B is equal to 0. Now A is equal to 1, 0, 0, 0. B is equal to 0, 0, 0, 1. Therefore, A plus B will be equal to 1, 0, 1. Identity matrix. Then your determinant of A plus B will be equal to 1 minus 0 is equal to 1. But it should be 0. Therefore, not a subspace. So this is not a subspace. So now second part. In this you can also prove that determinant of CA will be equal to, when you take out by property C squared into determinant of A. Determinant of A is 0, so determinant of C is equal to 0. By this we can say that it belongs to W, but this property is not satisfied. Next, second part. W consists of all matrices such that A square is equal to A. So now A square is equal to A. So let A comma B belongs to W such that A square is equal to A and your B square is equal to B. So we can say that A plus B whole square is equal to A plus B into A plus B is equal to A square plus AB plus BA plus B square. Now we can say this part is equal to 0 and this part we can write as an A plus AB plus BA plus B. How? Let's see. So suppose let's say A plus B is equal to 1 0 0 1. So therefore your A plus B whole square will be equal to 1 0 0 1 square. We'll get it as 1 0 0 1. This will be equal to your A plus B by this formula. Therefore, your BA plus AB will be equal to 0 if your A plus B whole square is equal to your A plus B. A plus B. So this part will be equal to 0. So now, then we can say, but let's see, when we take A as 1 0 0 0 and B as 0 0 1 1. Now let's see what is A plus B whole square. It will be equal to 1. Let's erase this. So 1 1 0 1 1 1 0 1. So when we multiply it 1, then 2, then 0, and then 1. Is it equal to A plus B? Your A plus B will be equal to 1, 1, 0, 1. But here we are getting something else. Therefore, it is not equal to your A plus B. Your A plus B whole square is not equal to A plus B, therefore not closed under vector addition. Closed under vector addition. Now let's see for multiplication. Let me erase this. So now, in case of vector addition, let's say let A belongs to W2 and your C is belonging to R. Therefore, we know that A square is equal to A. Now CA whole square will be equal to C square. A square will be equal to C square A. Let's assume C as 2 and A 1 0 0 0. So your A square is equal to A, but your 2A square will be not be equal to 2A and will be equal to 4A. Not 2A but 4A. Therefore, not closed under scalar multiplication. So now this is what you have to prove first for vector addition and then for scalar multiplication and then for zero vector also. So 0 square is equal to 0 0 0 0 0 0 0 0. When you multiply it, you get the zero vector again. Therefore, it belongs to W. But two other have failed. So not a subspace, not a subspace. So now this is the next question. So this is saying describe the span of each of the following. So you have U1 and U2. So I taught you alpha 1 U1 plus alpha 2 U2. I calculate in this way. So alpha 1 into 1 0 0 0 plus. So then alpha 2 into 0 0 0 1. So this we can write as alpha 1 plus 0, then 0, then alpha 2. So diagonal matrices, so this is basically showing the span is showing diagonal matrix where alpha 1 and alpha 2 belonging to R. Then your second part, mu1 is equal to 1, mu2 is equal to x, and your mu3 is equal to x square. So alpha 1 into 1 plus alpha 2 into x plus alpha 3 into x square. So this is showing alpha 1 plus alpha 2x plus alpha 3 x square. You can also write it as alpha 3x square plus alpha 2x plus alpha 1. So therefore we can write the span is showing set of polynomials with degree at most 2. So this is your answer. So next question. So this is your next question. This is saying in P2 determine whether this is the span of P of x comma Q of x. So 1 minus 4x plus 6x square. How will we do? We are given P of x and Q of x. Alpha 1, 1 minus x plus x square plus alpha 2, 2 plus x minus 3x square. Let's open up. So when we open up, we'll get alpha 1 plus 2 alpha 2 plus taking x common minus alpha 1 plus alpha 2 x plus alpha 1 minus 3 alpha 2 x square. Now what we can do, compare the coefficients. So on comparing we get alpha 1 plus 2 alpha 2 is equal to 1 minus alpha 1 plus alpha 2 is equal to minus 4 and alpha 1 minus 3 alpha 2 is equal to 6. So these are the three equations. On solving them you will get alpha 2 equal to minus 1, alpha 1 equal to 3. So we can say that it can be expressed as the linear combination of P of x and Q of x. So final answer should be written in this form: 1 minus 4x plus 6x squared should be equal to 3 into 1 minus x plus x squared plus minus 1 into 2 plus x minus 3x squared. In this form the answer should be shown as linear combinations. So next question. So next question is determine whether sine 2x is in span of sine x and cos x, P of x, Q of x. Earlier also we had seen one question. Now first of all write sine 2x in terms of sine x and cos x. We want a linear combination if it's a span. But here we are able to see that it's not as a linear combination of alpha 1 u1 plus alpha 2 u2. It is not in this form. Therefore, expression is a product but not a linear combination. If we had sine 2x is equal to alpha 1 sine x plus alpha 2 cos x, this is correct. But we are not getting that, so no is the answer. Next question. Express the linear dependence or independence in the following sets. The set of matrices given are A, B, C. So let's write alpha 1 into 1 0 1 1 plus alpha 2 into 1 1 minus 1 0 plus alpha 3 into 2 1 0 1 equal to 0 0 0 0. Write the four equation: alpha 1 plus alpha 2 plus 2 alpha 3 equal to 0, alpha 1 minus alpha 2 equal to 0, alpha 2 plus alpha 3 equal to 0, and alpha 1 plus alpha 3 equal to 0. By these equations, we can say alpha 1 is equal to minus alpha 3 and alpha 2 is also equal to minus alpha 3 by this equation. So when you substitute, you will get alpha 2 plus minus 2 alpha 2, therefore equal to 0. Therefore, we can say alpha 2 is equal to 0 equal to alpha 1 and alpha 3. If alpha 2 is 0, we can say by these two that alpha 1 and alpha 3 is also 0. So we know when alpha 1 is equal to alpha 2 is equal to alpha 3 equal to 0, therefore Li. But this is not an Li. Why? We could have said that it's an Li, but let's say if we had alpha 3 equal to 1, alpha 1 equal to minus 1, and alpha 3 equal to minus 1, then therefore we can have more than one solution. Therefore, it is LD. You have to check for many cases. It's not that you're getting just the 0 0 case done, it's an Li. No, that is not the case. You'll have to check, is there any other solution? If there is, therefore non-trivial solution. Next part, let's see. Next part is of polynomial where it's saying p of 2 of x is equal to 1 plus x comma x plus x square comma 1 plus x plus 2x square. So alpha 1 into 1 plus x plus alpha 2 into x plus x square plus alpha 3 into 1 plus x plus 2x square equal to 0. Now coefficients alpha 1 plus alpha 3 plus alpha 1 plus alpha 2 plus alpha 3 into x plus alpha 2 plus 2 alpha 3 into x square is equal to 0. Now comparing coefficients, alpha 1 equal to 0, alpha 1 plus alpha 2 plus alpha 3 is equal to 0, and alpha 2 plus 2 alpha 3 is equal to 0. Now this can be written as alpha 1 is equal to minus alpha 3. And here we can write alpha 2 is equal to minus 2 alpha 3. Now putting it in the second equation, we have minus alpha 3 minus 2 alpha 3 plus alpha 3 equal to 0. Therefore, alpha 3 is equal to 0, alpha 1 is equal to 0, and alpha 2 is also equal to 0. Now here we can say that it's a Li, linearly independent. These set of polynomials. Next question. So this is the next question where it's saying if V is equal to X, Y, Z, W belongs to R4, then these 1, 2, 3 equations is the subspace of R4, then we have to find dimension. This is a question of dimension. So here how will we solve it? Vectors. Vectors, you'll write the equation in form of vectors, we'll get 1, minus 1, minus 1. Put them horizontally. I'll write it in a neater way. So I'll write it here. A is equal to 1, minus 1, minus 1, 0, 0, 1, 1, 1. Then 2, 1, minus 3, and minus 1. Now on applying the form R3 minus 2R1, first let's apply this. Then you'll get 1 0 0 minus 1 1 3 minus 1 1 minus 1 0 1 minus 1. And similarly, when you solve it using your row operations, you'll get it as 1 0 0 minus 1 minus 1 0 1 1 1 0 1 1. So now here non-zero rows are number of non-zero rows. R3 and your rank of A is also equal to 3. Therefore, your dimension will be equal to your number of variables. How many variables? 4 minus your rank is equal to 1. So, your dimension of V is equal to 1. This is your answer. So basically, first you'll have to form a matrix. After forming the matrix, you have to solve the matrix until you get to the final state where it's simplified in form of zeros at the lower end. So after that, you see for non-zero rows, see the rank, and then calculate the dimension. So next question. So this is the next question where it's saying for each of the following, find its basis and dimension. So in the first question, take common for take common there are two A's and two B's. When you take common, you'll get a linear combination of the polynomials. And these linear combinations, let's write them. So A into 1 plus x cube plus B common x minus x square. Therefore, any element of W1 can be written in this format. And this is linearly independent because neither can be expressed as the scalar multiple of the other. And basis, let's write basis of 1 is equal to 1 plus x cube, comma, x minus x square. Dimension of W1 will be equal to 2. Those who are not able to understand this can refer to my previous video where I've explained what are bases, how to calculate them, and further how to see for dimension. So this is first part, then second part. Second part says these two matrices are given. So let's see. Alpha 1 into, take A part separate and B part separate. Let's not write alpha 1 and alpha 2 because here we have A1 and B, A and B. So A1, here we don't have A, here we don't have A, here we have A. Then B 0 minus 1, then 1 and then 0. So A and B can be written in this format. Therefore, any W2 can be, any element, any vector that is in W2 can be written in this format. And therefore, your bases are, wait a minute, so 1, 0, 0, 1 and 0 minus 1, 1, 0. And therefore, your dimension of W2 is equal to 2. So third part. Similarly, in third part also, you can express them as A into 1, 0, 0, 1 plus B 0 minus 1, 1, 0. When you express them equal to 0, comma 0, it will come out to be linearly independent. Just check that. And basis. So basis set can be written. So 1, 0, 0, 1 and 0 minus 1, 1, 0. And therefore your dimension of W3 will be equal to 2 based on the basis. Express. So basically when you get a question on basis and dimension, first of all try to write in terms of a linear combination. I follow this format alpha 1 u1 plus alpha 2 u2 and so on. So you try to write it like this, and these type of questions are very important that we are doing. Like this question is very important in from exam point of view, and also the previous questions that we have done, these all are important questions. So let's move on to our last question for today. So this is our last question. In this, we say if A is equal to this matrix and your V is equal to X, Y, Z belonging to RQ such that the determinant of A is equal to 0. Therefore, you have to find the dimension of V. How will you find the dimension of V? Now, let's see when you calculate the determinant of A, let's calculate it. So 1 into 4 minus 3y plus minus 1, 4 minus 3x plus 1, 2y minus 2x. So when you solve, you'll get x minus y. Now here we are saying determinant A is equal to 0. Therefore, your x is equal to y. Now, r cube x, y, z. Here we say x is equal to y, so x, x, z. So now, can x, x, z be as written as a linear combination? Yes. How? 1, 1, 0 plus z 0, 0, 1. Therefore, linearly independent and basis. Basis can be written. So this is your homework. Write the basis. I have written the linear combination and the dimension of V is equal to these two things are your homework. I have solved the question. The only thing is to interpret the result and write the answer. First of all, you calculate the delta, the determinant of A. Then after that, you satisfy the property given in V. When you satisfy the property, try to write in form of a linear combination. When you've written that, the answer is done. Just write the basis and dimension and done. So thank you everyone. I hope these questions were nice and got a clear idea of vector spaces. So if you have any doubt, feel free to write in the comment section. If you like the video, do like, share, comment and subscribe to my channel. And also write the answers to these two bases and dimension of V for the last question. So thank you. Bye bye.